Hello, everyone, and welcome to the show. I'm Max, and this is Frames and Other Delusions, Episode 7 of PQ adic analysis and the Collatz Conjecture, a video series I'm making to accompany my 2022 PhD dissertation of the same name. This episode is going to be a little bit different from the ones that have come before it. In Episode 1, I showed you the main punchline of my discovery that we have these F series that have these convergence properties that we'd have never seen before. And then in episode 2, I gave a background as to what I'm doing. And episode 3, I then constructed the Newman chi-q of the shortened qx plus 1 map and proved the correspondence principle. Since then, with the exception of my proof of the PQ adic Wiener-Tauberian theorem, everything that I've been covering is pretty stuff that's either already bit known or very close to what we already know, and my contributions are either minor new things or it just happens to be a matter of how I frame the exposition. In this episode, though, we're going to be stepping fully into the area of entirely new mathematics. So we're going to be talking about how to create new ideas rather than trying to apply ones that we've already seen. To that end, I need to put an asterisk in front of this episode. Though I've made significant progress, especially in the past few weeks, with whipping these ideas into shape, this is still an in-progress material. Then there could be potentially be further improvements down the line. Indeed, this episode can be now itself should be given priority over anything that I wrote in my frames paper, because this episode is now a further refinement of that material. So, the prelude. To begin, let's go back to where we started in episode 1, which is with the F series for chi-q. To simplify matters, let's just get rid of these constant terms over here and consider this F series, S2q, where for the moment, q is an odd prime number. Our analysis in episode 1 showed that this series converges q-adically if z is in z2 prime, where recall z2 prime is two adic integers that are not non-negative integers. We also saw that S2q converges in the reals if z was a non-negative integer. The recipe for summing this series in this way is something we called the simple 2q adic frame, and denoted by this symbol, whose presence here means that this side is supposed to be interpreted according to this recipe, depending upon the value of z. At this point, S2q is really a formal expression. Essentially, it's a cousin of formal power series, rather than an instance of a rigorously defined function with a specified domain and codomain. Indeed, as we'll see, the algebraic properties of how this function behaves, particularly with interactions with self-maps of Z2 prime, of Z2, will be quite important to understanding its behavior. Nevertheless, what this recipe tells us is that it gives us a way to take this formal series and turn it into a function. In particular, if we sum this series according to this convention, we saw in episode 1 that the result will always be a q-adic integer. As such, we can turn the formal series S2q into an honest-to-goodness function, x2q, from the two adic integers to the q-adic integers, where we define x2q by the rule that the sum of the series it's equal to the sum of S2q in the q-adics when z is in z2 prime, and is given by the sum of S2q in the reals if z is a non-negative integer. Now, let's just need to give you a bit of background. So, classically, when you're doing analysis, this means you're going to be working with functions whose outputs, and often inputs, can be understood in terms of numbers. Here, by number, I mean an element of the real numbers, the complex numbers, or other complete valued fields, and the algebraic structures that we can build on top of them. Of particular import here are the Banach spaces, which in a sense are basically the lingua franca of modern analysis. You can get pretty much everything in an analysis fits into a Banach space somewhere, or into a generalization of it. When studying spaces of functions, one of the things we learn in analysis is that the topology, that there is a way to assign notions of convergence, and that these are associated with and indeed induce different topologies. We can have any introductory course in modern analysis will be rife in. Sorry. So the idea is that a sequence of functions, might converge in one topology, but not in a different topology, is completely standard. As I was just about to say, any introductory course in modern analysis will be rife with examples for students to learn of sequences of functions that, for example, converge in LP norm for some p, but diverge for others. Then, of course, there's the well-established notion of different modes of convergence. A sequence might converge point-wise almost everywhere on its domain, but fail to converge uniformly on its domain. A sequence might converge uniformly on every compact subset of its domain, but fail to converge uniformly on the entirety of its domain. Comparing different modes of convergence is a mainstay of mathematical analysis. We have LP convergence, uniform convergence, pointwise convergence, convergence in measure, almost everywhere convergence, weak convergence, weak star convergence, the list goes on. So in analysis, the idea of considering sequences of functions and different ways that they can converge is not new. However, while these different topologies can often be extraordinarily different from one another, there's still one common denominator that holds them all together. Namely, that the field that the fn's spit their values into remains fixed. If we're talking about a sequence of real valued functions, we can consider whether it converges in LP, converges uniformly, converges almost everywhere, etc. But ultimately, all of those different forms of convergence take for granted that the functions are converging in a Banach space or some other topological space built over the real numbers. Okay. However different LP and LQ might be for depending on P and Q's values, nonetheless, both spaces will exist over the same field. However, as our work with S2Q and chi-Q shows, in PQ adic analysis, we can no longer take this for granted. In addition to classical distinctions between different modes of convergence, like pointwise versus uniform, F-series require us to consider topologies of convergence generated by different absolute values on the underlying field. Thus, we can consider the 3 adic absolute value, the 5 adic absolute value, the real absolute value, etc. All of those are different absolute values defined on the underlying field of rational numbers. Just to show that what I'm doing here isn't really that novel once you take a deep enough look at it, let's remember what the modern definition of a function is. This is generally attributed to Dirichlet, which is that it's a rule f, which to every element x of the input set, called the domain, produces an element f of x of a set y, called the target space or codomain. In this view, a formula for computing the value of a function as certain inputs is merely a representation of the function, and one function may have multiple different representations. For example, one writes zeta of s to denote the Riemann zeta function. The Riemann zeta function is known to be defined for all complex numbers except s equals 1. We also have the most well-known representation of that function, the Dirichlet series here, which happens to converge for complex numbers s whose real part is strictly greater than 1. This is then it can be considered a local representation of the zeta function. This is equal to the zeta function on some domain, but not equal to the zeta function on its largest domain. And indeed, as we all know, you can make sense of zeta of s for which this series converges. And so as a result, we learn in university that when we talk about functions, we need to keep distinct in our minds the function as an abstract object and a particular formula which represents it. This same reasoning applies to x2q. it is perfectly well defined as an abstract rule. For every two-adic integer z, I get a q-adic integer x2q of z. The series S2q that we use to get x2q is just a particular representation, and it turns out that this representation happens to require an unusual mixing of topologies in order to figure out its sum. So as a first step toward generalization, let's consider the following expression. SPQ of z, which I'm denoting by this sum here. It's p to the n, and here it's q to the number of 1's digits in the projection of z mod 2 to the n, where here z is a two-adic integer. To be clear, this is not a function. It is a formal expression which we have to work with in order to figure out where and how it can be defined as a function. So now let's actually just do this. Let p and q be coprime non-zero integers. Let z be in z2 prime, and let L be any prime number. Then this series is going to converge L-adically if and only if L is coprime to P, and if Q has an L-adic absolute value less than 1. Moreover, when it converges, this SPQ of Z will necessarily be an L-adic integer. 2, let Z be in the non-negative integers. Then SPQ will converge in the reals if and only if P as a prime as an integer is greater than 1 in real absolute value. Moreover, when convergent, SPQ of Z will be an element of Q, a rational number. Also note that this thing can be proved for non-zero algebraic integers, PQ, provided that the ideals generated by P and Q in this field are coprime in that field, meaning that there's no prime ideal of this non-trivial which contains both of those. So the proof, let P and Q be coprime, etc. Then let L be a prime number. So pick a Z in Z2 prime and suppose SPQ of Z converges in QL. So, as an example, we can choose z equals -1, then the convergence gets us this. More generally, the observation is that if you pick z in z2 prime, then the number of digits, of 1's digits, in the projection of z mod 2 to the n, as n goes to infinity, will tend to infinity. So whatever z we pick, as long as z is in z2 prime, the exponent of q here will grow without bound. Since this converges, it must be that q over p is less than 1, an L-adic absolute value, or some power of p is less than 1, and in the end we get what we need. More generally, if it's convergent, then it must be that p and q both have L-adic Q has an L-adic absolute value less than 1, and that P has an L-adic absolute value greater than or equal to 1. Actually, equal to 1, because otherwise it will diverge for a given prime. So that works out. And so for here, suppose the other direction, suppose that P has an L-adic absolute value of 1 and that Q has an L-adic absolute value less than 1, then letting Z and Z2 prime be arbitrary, we take the L-adic absolute value and we get this. And again, because Z is in Z2 prime, it has infinitely many 1's digits, so this tends to infinity. Just more generally, it's just the fact that in this formula, this is going to converge this series is going to converge L-adically for a prime L if and only if this goes to 0 L-adically, which then immediately gives us the condition that we need. Yeah. Likewise, the fact that this is going to be an element of QL, is the trick, in particular in ZL. The trick is to note that because P and Q are both rational numbers, and since QL is an extension of Q, and since it's metrically complete, if this series converges L-adically, it's necessarily going to converge to an L-adic number. In particular, we get that it's going to be an L-adic integer if because P is co-prime to L, and thus and ZL, the set of P of L-adic integers, is also a complete metric space. The convergence in the reals for Z and N0, on the other hand, it's just like we saw in episode 1. What happens is for any given non-negative integer Z, the numerator here, its exponent, will stop growing once n is bigger than the number of two adic digits of Z, and so we end up getting a convergent geometric series, which will converge in the reals as long as P is greater than 1 in absolute value. Likewise, since it's a geometric series, we can find its sum explicitly, which is this thing, and we see that this is indeed a rational number. So this definition discussion then motivates the following definition. Let P and Q be co-prime non-zero integers, let L be a prime number, and suppose that P is absolute value greater than 1, real absolute value, that P has L-adic absolute value equal to 1, and that Q has L-adic absolute value strictly less than 1. Then we'll use this recipe to turn this F series into a function. And this function is going to take values in, it's not just going to be this is going to be not just be Z2 to QL, it's going to be a function from the two adic integers to the L-adic integers. Having elucidated some of the convergence properties of this F series, we can now introduce the simple PQ-adic frame. Let P and Q be distinct prime numbers, and consider a sequence of functions, Fn, from Zp to Q. I say the Fn's converge to some function f from Zp to Qq with respect to the simple PQ-adic frame, denoted by this, whenever the value f always takes, whenever the limit function takes rational values on the non-negative integers, and whenever the limit function, the sequence converges to the limit in QQ if Z is in Zp prime, and meaning that it's a p-adic integer, which is not a non-negative integer, and that the limit converges in the topology of the reals if Z is a non-negative integer, and of course that the limit is an element of Q. I write FPQ to denote this frame, and then it comes in handy when discussing the convergence of functions like XPQ. This right here, it's F2Q because this is a function which accepts a two-adic integer as an input and produces a q-adic integer as an output. And so this is, and again, as I was originally motivated in my dissertation, this notation is very nice because it's more elegant and less cumbersome than having to constantly qualify our work by reminding the reader of the particular convention we've chosen to make sense of the series. But frames turn out to be more than just a notational convenience. They're in fact a gateway to an entirely new class of behaviors. So as of the time of this recording, this episode is my third trip through frame theory. My first was in my dissertation, while my second was in my frames paper, my first ever mathematical publication. The treatment given in this video is the most recent version of my ideas, and where it conflicts with the previous two treatments, this treatment should be given precedence. So in the course of writing the script of this video, I discovered yet another way to frame frames, pun intended, and we'll get to it in a bit. But however, for now, let's just start with what I originally had in mind, where this is basically what I give in my frames paper, albeit with some modifications courtesy of Algebra Moloch. So, definition. Let X be a set and K be a field. Ideally, I think I want K to be a global field. But anyhow, a K-frame F on X is a map which to each point of X produces a F of X, which is an element of KV. Recall that KV is the set of all completions of K. In particular, it's equivalence classes, and this is in a one-to-one bijective correspondence between the set of completions of K and the set of places of K. So in particular, F of X is going to be a valued field whose absolute value comes from one of the places of K. So F accepts a point of X as its input and produces a valued field as an output. Also, just for future reference, I will speak of X as being the support of F and denote it by support of F. I'll sometimes omit reference to the underlying field K or the underlying set X and simply speak of a frame when either K or an X are known by context or are not relevant to the discussion. In practice, K will be a discrete field with a trivial absolute value, and it's going to be a global field, although it can also be Q bar or closures. But anyhow, so Q global fields is Q finite degree extensions thereof, a function field, finite degree extensions thereof, and of course their algebraic closures. So from this point on, unless specifically stated otherwise, we're going to be fixing, for this section, we're going to be fixing a set X, a global field K, and a K-frame F on X. In my frames paper, I required X to be a topological space. I do not believe this is necessary. So, warning. The construction of completions of K using absolute values picked from places has significant interactions with the algebro-numero-theoretic issues we discussed in episode 6. So this is get technical details. In this case, we get so for as an example, if we consider K equals Q root 7, this example I wanted to write it up, but it doesn't quite work because my assertion that there are two different embeddings of this in Q7 is not true. Actually, this reduces to a single power of an ideal, which means that in number theory terminology, 2 ramifies in Q root 7. Anyhow, so when in practice, when we're dealing with the different completions, we need to take care which completion we specify, because depending on the embeddings, an expression like 3 minus root 7 or 3 plus root 7, its absolute value might vary depending on how we embed it. An example of this is that if we want to consider the real completion of Q of root 7, there are actually 2 different absolute values we can pick. One that gives this and one that gives the absolute value of its conjugate. So, and these are also inequivalent. So when we're working with our frames, we need to be careful that we're not just specifying a completion, we're specifying an embedding of the underlying field K in the completion f of x. So in our standard example is let P and Q be prime numbers. Then the simple p-q-adic frame is a Q frame on the p-adic integers, which outputs the real numbers with the real absolute value if z is a non-negative integer, and outputs the q-adic numbers with the q-adic absolute value if z is in z2 prime. The reason we need frames is to make sense of functions like chi-q, which have series representations whose topologies of convergence vary from point to point. In the general setup, the functions we will use frames to interpret will accept elements of our topological space X as inputs. But this leads to a natural question. Unlike the formal series SPQ, we want our functions to be actual functions, so that means it's not enough just to specify their input space, X. We have to also specify the set where functions will take their values. With chi-q, we saw that all of its outputs were q-adic integers, and so in that case at least, we could get away with saying that our frame will be associated to functions from x equals zq to, x equals z2 to QQ. However, this turns out to be insufficient. So the simple p-q-adic frame tells us that this is we're going to be using the real topology if although we, in addition to the standard p-q-adic frame, we can also use a different one. For example, consider this choice where SPQ of z will be summed in the real topology whenever this limit condition holds, and it will be summed in the q-adic topology whenever this limit condition holds. These limit conditions arise from applying the root test to the nth term of this series, and so what this particular convention I've defined here is telling us is, what if we consider the case where our frame says we will sum the series in the real topology for any 2-adic integer z for which it happens to converge in the real topology. So for example, just in looking at the formula, note that in order for this to converge in the reals, the number of ones in the projections of z mod 2 to the n needs to grow relatively slowly as we increase the value of n. So if we picked, say, z to have a digit sequence that it's 1 followed by 2 zeros, followed by 1, followed by 4 zeros, followed by 1, followed by 8 zeros, etc., something like that, then such a two-adic integer will make this series converge in the reals. But also notice that such a two-adic integer is going to be irrational. And as a result, there's no way to guarantee that the sum to which the series converges in the reals will be a rational number or even an algebraic number. So if we, the reason why we were able to get that rationality when we are considering SPQ is because of the closure of the q-adics under, and the fact that when we were in the input in the non-negative integers, we could use the geometric series to tell us that yes, even though the series is converging in the reals, the sum ends up being a rational number. So in general, we're going to have to deal with the problem that our functions that we make sense of with frames don't necessarily do so in a way that they spit out all of their numbers into a single set. As such, we're going to need what I call the image of a frame. Specifically, the image of the frame f is going to be the union of all of the f of x's. So that means I of f is the set obtained by taking the union of all of the fields that f specifies as we consider different points of big X. Here, I of f is only a set. It does not come with a topology. Nevertheless, since f of x is defined to be a completion of k for every x, observe that this intersection is going to be a field because the intersections of any two fields is a field, and it will contain k as a subfield. Consequently, I of f contains k as well. So for the image of the simple PQ adic frame is R union QQ. So with the concept of an image of, and also just ignore this, it's extra details, it's messy. I should have probably cleaned this script up a little bit more before I started recording, but whatever. So with the concept of the image of a frame, we now have a set that our functions can take values in. So the setup is that the functions we'll be studying are ones of the form f from x to the image of f. This leads to the definition of what I call a compatible function. A function is compatible with a frame, or equivalently, a frame is compatible with the function if f of x is contained in big F of x for all x in big X. That is to say, everything agrees pointwise. This pointwise philosophy turns out to be absolutely critical in frame theory in general. So I will write C of f to denote the set of all f compatible functions. Additionally, if given a function f from x to y, where y is a set, I say f is compatible with f if y is a subset of I of f, and f is compatible. In other words, every output is contained in the image of f, and the f is compatible. So with this, we can then get the notion of convergence with respect to a frame. Consider a function f it's compatible, and with our frame, and I say a sequence fn of compatible functions converges to f with respect to our frame if for every x, fn of x converges to f of x in the topology specified by the frame at x, which I denote this convergence by writing this, or specifically this, and then specify the set. So in practice, the compatible functions we will work with will arise in the following way. We'll have a valued field, k, typically a number field, equipped with the trivial absolute value, and an infinite series f of x, which is a sum of fn's, where the fn take values in k. Note then that this is a key observation. If your function takes values in k, it's going to be compatible no matter what, because K is a subfield of big F of X for all X. So the idea here is that we pick a K-frame of F so that for every X, this happens to converge in some completion. In many nice cases, like with XPQ or ChiQ, I of F will turn out to be overkill. In these cases, the functions of our compatible functions can be confined to some particular completion of K, which I'll call K prime. And then that is F of X will be in K prime for all X and X. In this way, F can be realized as a function taking values in a field rather than in a union of fields. This idea is important enough that it deserves its own name. Let K prime be a completion of X or the ring of integers of such a completion of K or the ring of integers of such a completion. Given a compatible function F, I say F condenses over K prime, or probably say condenses into K prime, if F of X is contained in K prime for all X and X. And then I write CK prime of F to denote the set of all compatible functions that condense into K prime. So as an example, let Q be an odd prime and consider the simple 2q-adic frame F2Q. By our analysis of the above, not only is X2Q compatible with F2Q, it also condenses into QQ, and in particular into ZQ. Now, a great deal of the power of classical modes of convergence, uniform, LP, etc., comes from the fact that these modes of convergence are related to norms, and that we can then get Banach spaces by considering all of the functions which are well behaved with respect to those norms. And if not norms, then they come from semi-norms, in which case we can obtain locally convex topological vector spaces. The most famous instance of this is the space of test functions, whose dual yields the space of tempered distributions. We'll be saying a lot more about locally convex spaces in a moment. But for now, this infrastructure is important to us because it sets the stage for investigations using more abstract approaches, like from functional analysis and even more algebraic subjects. As such, in the hope of attaining greater understanding, and for sheer practicality's sake, it makes sense to look for function spaces where F-series can be treated not just systematically, but also in greater generality. Unfortunately, the peculiar convergence properties of F-series make them highly pathological by classical standards. Indeed, even this space of compatible functions that we've come up with, it can be potentially quite unwieldy, because we could have a function that takes a value, a real irrational value at one x, and then a p-adic irrational value at another x, and those quantities have no way to interact with one another in a nice way. So this immediately, of course, we want to ask, how, if at all, can we add different functions together, different compatible functions? Can we multiply them, etc.? To say nothing about more complicated operations like integration or convolution. And fortunately, this is where frames really shine, because not only do they give us a means to talk about the convergence without encumbering ourselves with all the details, they also allow us to construct spaces that are very well behaved where our F-series naturally and comfortably exist. And the secret to making all of this work is to just keep thinking pointwise. Let F be a K-frame on X and just fix some point X. Letting little f and little g be compatible functions, note that f of x and g of x are both elements in the field big F of x. As such, their sum and product are also going to be elements of the field big F of x. And continuing to think pointwise, this recipe works perfectly well for any x we pick. The compatibility condition is then what guarantees that expressions like these will be well defined as functions, because no matter which x we pick, the resulting realizations of these functions as f of x plus g of x and f of x times g of x will occur in a single field. And so in doing so, we've actually shown that f plus g and f times g are going to be compatible functions. So this tells us that c of f has the structure of a commutative unital ring under the operations of pointwise addition and pointwise multiplication. Now something to note: the additive identity element of this ring is the constant function 0. To each x, it outputs the 0 of f of x. Ordinarily, if you have two completely different fields, there's no way to compare their 0 elements. For example, the 0 element of a finite field doesn't really make sense in a context of a field of characteristic 0. However, all of these fields here aren't arbitrary. They're all completions of K. So this 0 isn't just any 0, it's the 0 of K. Likewise, we can take the 1 of K will be the 1 of f of x for all x. So the constant function 0 is the additive identity element, and the constant function 1 is the multiplicative identity element. And so the proof of the proposition is, it brings up a key point. Because the fx's are completions of K, K ends up being the common thread relating the values taken by any given compatible function. In particular, we can then upgrade C of f from a ring to a K algebra. Moreover, this same argument works for any subfield of K. Anything which can act on K can then act on a completion of K. Now, this can likely also extend to rings with an action on K, and that gives K the structure of an R module. So let K be a field, let F be a K-frame, and let blackboard F be K, or any subfield thereof. Then the space of compatible functions is a unital algebra over blackboard F with pointwise addition of functions, scalar multiplication of functions by elements of blackboard F, and pointwise multiplication of functions as the addition, scalar multiplication, and algebra multiplication operations, respectively. So this is really nice. In fact, by the same reasoning, we can get an algebra structure for the space of functions that condense onto K prime. This is frames in a nutshell. We have our assignation of topologies to points of x, a space of compatible functions, and a notion of convergence with respect to a frame. I originally conceived of frames in this way, and this is how I present them in my dissertation and in my frames paper. However, on March 11th, 2024, my 32nd birthday no less, I discovered a way to combine these three facets of frames, assignation of topologies, a space of compatible functions, and a notion of convergence. We can combine them all into a single object, a metrizable topological vector space. So just to review, for those of you who don't know, let K be a topological field, and let V be a vector space over K, which is also a topological space. We say that V is a topological vector space whenever the vector addition operation and the scalar multiplication operations are continuous in the topology given to V. If, in addition, there is a bilinear operator on V taking values in K, which is continuous, we then say that V and B is a topological K algebra. Because any one-dimensional subspace of V is isomorphic to K as a vector space, it must be that when we take the topology on V and then use it to give K the subspace topology it inherits from V, it must be that this subspace topology is then the same as the topology which K itself was given to begin with. So, topological spaces occur everywhere, and I'd have to argue that they're probably as far as I'm willing to go as a mathematician. In fact, I'd prefer to have at least a locally convex one, just because I like adding things, integrating, computing sums, etc. So topological vector spaces let me do that. The classic example is R with its usual topology, as is RD. Indeed, any valued field is automatically a topological vector space over itself when we give it the topology induced by its absolute value. And we can then take D copies of K, multiply them together using the Cartesian product, and then that gives us a topological vector space where the topology is the product topology. All Banach spaces are topological vector spaces, where the topology is, of course, the one induced by the Banach space's norm. The reason why people study topological vector spaces instead of just limiting themselves to Banach spaces is because functional analysis, where TVSs most commonly arise, sometimes has to deal with vector spaces whose topologies do not come from norms. Also, just as a reminder, TVS means topological vector space. So locally convex vector spaces, also known as locally convex spaces or locally convex topological vector spaces, like the space of Schwartz functions from harmonic analysis, are among the most important examples of topological vector spaces which are not Banach spaces. The Schwartz space, recall, named after Laurent Schwartz, it's the space of all functions that more or less look like the Gaussian bell curve. They decay rapidly as there are functions on the reals that decay rapidly as x goes to positive or negative infinity, and moreover, their derivatives of arbitrary orders also decay rapidly. And the reason why they're so important is because the Fourier transform is an isomorphism of Schwartz space onto itself. However, because of the condition on all of those different derivatives decaying, we're not able to realize Schwartz space as a normed space. Instead, we use seminorms. So recall a seminorm it's a norm that is not positive definite, meaning that there are elements which can have value 0 when you plug them into the seminorm, but those elements are themselves not the 0 element. The classic intuition for this is that just when you're working in, say, a finite dimensional vector space, like a R3, we can get a norm on R3 by taking the sum of the squares, by taking the square root of the sum of the squares of the entries of a vector. The norm then is something which depends on all of the components of our vector. A seminorm, on the other hand, would be, for example, a function which accepts a three-dimensional vector and produces the absolute value of its x coordinate. In that particular setup, we have that any function that has a 0 x coordinate will then have a 0 value under the seminorm, but any vector that has a 0 value for its x coordinate will have a 0 value for its seminorm. However, there are lots of vectors that have zeros in their x components that are not the 0 vector in R3. And so, simply put, we're going to be using the seminorms to construct topologies later on, so that's quite useful. So let's just now introduce metrics, though. A metrizable topological vector space, MTVS, is a pair VD, where V is a topological vector space and D is a metric on V, so that the topology induced on V by the metric is precisely the topology that V was given. Equivalently, an MTVS is a vector space with a metric D, so that the metric induces a topology on K, where K is viewed as a one-dimensional subspace of V. An isometry of metrizable topological spaces, V dV, W dW, is a linear map from V to W so that the W distance between L of X and L of Y is equal to the V distance between X and Y. When such a map exists, V and W are said to be isometric to one another. So, also just apologies if my voice sounded weird for a moment back there. It was because I was having a bloody nose, but now everything is back under control. So anyhow, we have our metrizable topological vector space, and so this is a proposition, an isometry of MTVS's is a homeomorphism, meaning that it's a continuous map and it's bijective, and the inverse of such a map is again an isometry. So as I said, frames turn out to be realizable as MTVS's. To show this, we're going to come up with a norm-like function on our space of compatible functions and demonstrate that it has the properties needed to create a metric whose notion of convergence is the same thing as convergent with respect to a given frame. So let X be a topological space. And do we need X to be? No, actually, no. Let's let X be a set here. It doesn't need to be a topological space. Let X be a set and let K be a field. I write x to the k to denote the set of all functions from x to k. This becomes a k algebra when equipped with the operations of scalar multiplication, pointwise addition, and pointwise multiplication. Now let f be a k-frame on x. For each for each point x, I'm going to define a map fx from xk to the non-negative real numbers, and it's the following rule. Given a function in xk, I will write this as in this terminology, and what it means is it takes f, evaluates it at x, and then applies the absolute value specified by the frame at x. I then define xkf as the set of all functions from x to k, such that the supremum over all x and x of this is bounded. This here is, I call this the f norm. This is the supremum of this, and this is a semi-norm here. So in this case, we're going to be using our semi-norms, and these are quite important. What these do, again, is that they take a function, evaluate it, and then apply the associated absolute value. And the reason why we need to define x, f, kf is because we then have that the f norm is then well defined on this space. Note that not every function in xk is contained in xfk, because these functions have to be pointwise bounded with respect to the frame, whereas such a function here, a function wouldn't be. So, for example, if we were considering the simple simple pq-adic frame on ZP, you could have, if you have a function which is equal to n at every non-negative integer n, so that means f of 1 is 1, f of 2 is 2, f of 3 is 3, etc., then although that function is pointwise bounded on the non-negative integers, if you take the supremum of the real absolute values of all of those numbers, it's unbounded, and so that function would not be in xfk. So, although I call this the f norm, it is not a norm in the sense of Banach spaces. This is because for a Banach space x over a complete valued field k, a norm must possess the property of absolute homogeneity, meaning that if x is a Banach space, and here's its norm, it must satisfy the property that for all vectors x and for all scalars alpha, the norm of alpha x is equal to the k absolute value of alpha times the norm of x. In general, the f norm fails to satisfy this property precisely because of the multiple different completions of k that we use in creating our frame. Indeed, the thing to note here is that in the language of functional analysis, when you define a norm or a semi-norm, you are working with a given vector space which occurs over a given field. So 99.999% of functional analysis, this is never questioned. We're going to we start with working over, say, a real vector space or a complex vector space, and then we define semi-norms, and they're going to be absolutely homogeneous, say, with respect to the complex numbers or with respect to the real numbers. However, because we're using different fields, we lose that absolute homogeneity. Indeed, in our frame theoretic setup, this isn't optional. That's the whole point. Because we use f of x as absolute value in defining the semi-norm, in showing that this is a semi-norm, we need to keep in mind that this is a vector space semi-norm acting on this field, not necessarily acting on k. And moreover, it might not work if you consider a field associated to a different x. However, this turns out to be no problem at all because we simply extend scalars. Because x to the k is a vector space over k, and because f of x is a completion of k, anything that we can do in k, we can also do in f of x because k is a subfield of f of x. And so, indeed, using tensor products, if we take the tensor of x to the k with a field outputted by a particular completion at a particular point, this is then the same thing as the functions from x to the field f of x. Just to see that in general the f norm is not a vector space norm, to see this, observe that if we fix a single x, then because only one field is involved, absolute homogeneity does in fact apply. This is because fx is a seminorm in this case, and it's a seminorm associated to this particular field. This holds for all functions x to the k and all alpha in k. To get the f norm, though, we're going to need to take the supremum of both sides of this thing with respect to all points of x. This gives us as follows, and unfortunately, the supremum of a product is not the product of the suprema. In general, the supremum of a product is merely less than or equal to the product of the suprema, and so we get that the f norm of alpha f is less than or equal to this times this. Here, what this is going to say is that this is the supremum of the possible absolute values that alpha has in over all of the fields that occur in our frame. Absolute homogeneity would require this to be an equality rather than an inequality. To see that the inequality cannot be dropped, let's just consider the case where k is the rationals, alpha is 1/2, and f is the constant function, which is 2. Then choose a frame so that there is points x infinity and x2, at which f of x infinity, that's the reals, and f of x2 is the two adics. Then alpha f has an f norm. This is 1/2 times 2, which is the f norm of 1. That's the supremum of the absolute values of 1, but 1 always has absolute value 1, so this is just 1. On the other hand, the product of the f norms, here, this is going to be the product of these two guys, and note that 1/2 fx is going to be 1 if f of x is qp and p is an odd prime, 2 if f of x is the two adics, and 1/2 if f of x is r. And likewise, 2's its absolute value, it's going to be 1 if y makes the frame if the frame spits out the p adics at y. It's 1/2 if the frame spits out the two adics at y, and it's 2 if the frame spits out the reals at y. So if we take the supremum over all x, the result is, for this value is going to be 2, and the result of this value is going to be 2, and so we get that their product is 4, which is strictly greater than the norm, f norm of the product. So the inequality can't be dropped. Despite this, although scholars of functional analysis would likely not call the f norm a norm, an algebraic geometer very much would, particularly if they happen to study Berkovich spaces. So let R be a unital commutative ring with additive and multiplicative identity elements, 0R and 1R, respectively. A ring seminorm on R is a map from R to the non-negative reals such that the 0 element has seminorm 0, 1 has seminorm 1, and we have that it satisfies the triangle inequality, and it is submultiplicative, meaning that the seminorm of a product is less than or equal to the product of the seminorms. If, in addition, it satisfies the ultrametric inequality with equality whenever these two are different, we say that this is non-Archimedean. Otherwise, we say that the seminorm is Archimedean. A multiplicative ring seminorm is a ring seminorm for which the product of the seminorms is the seminorm of the product. And a ring norm is a ring seminorm which is positive definite, meaning that the only element of the ring which has 0 seminorm is 0. And just, although we're not going to use it, in algebraic geometry, the Berkovich spectrum of the ring R, denoted M of R, is the set of all multiplicative ring seminorms. So, although it's not, to my knowledge, standard terminology, I will say a ring seminorm is submultiplicative when I want to emphasize that it is not multiplicative. That is, there exist f and g for which this inequality is strict. Additionally, if I want to distinguish between a ring seminorm and a vector space seminorm, I'll speak of ring seminorms and vector space seminorms. The major difference between a ring seminorm and a vector space seminorm is that the vector space seminorm has to have the absolute homogeneity requirement, meaning that for any scalar times vector has the seminorm is the same thing as the absolute value of the scalar times the seminorm of the vector. So in this case, every actually no, I don't think it's true. Whatever. So we're going to continue, and so fix x in x, then fx is a multiplicative ring seminorm on x to the fx, the functions from x to f of x, and moreover, the quality of fx, its Archimedeanness or non-Archimedeanness, is the same thing as the quality of the field f of x. So since this absolute value takes non-negative real values, so does f of x. Given any scalar alpha in the field, then any f in this space, f of x of alpha f, it's the absolute value of alpha times f of x, which is absolute value of alpha times the absolute value of f of x. This is the absolute value of alpha, and this is just big Fx of f. So that means it's absolutely homogeneous. And finally, the triangle inequality follows because this is an absolute value, and in particular, this seminorm will be Archimedean or non-Archimedean if and only if f of x is Archimedean or non-Archimedean, respectively. So this proves that fx is a vector space seminorm. To prove that it is also a multiplicative ring seminorm, observe that for any f and g, if we apply the seminorm, then because the absolute values are multiplicative, the product distributes and we get what we want. Now, fixing x, note that this space is both a vector space over the field big F of x and a vector space over k. This is like saying that a vector space over the real numbers is also a vector space over the rational numbers. In particular, x to the k, the functions from x to k, is going to be a subspace of the functions from x to f of x. Consequently, f of x descends from a seminorm on this space to a seminorm on this space. In particular, since x to the k is also a subring of x to the f of x, we then have that fx is a multiplicative ring seminorm on x to the k. And so this is where we're going to get our metric from. The map, which takes two elements of xfk and outputs the f norm of their difference, defines a metric on xfk. Moreover, pointwise multiplication of elements in xk is continuous with respect to this metric. For all of this, we need to note that for any f in xfk and any point x, we have that f is also an element of this space because, again, k is f of x extends k. So the positive definiteness. If f has 0 f norm, then the value that f takes at x for every x in our space must be 0. Since this is an absolute value, this can occur if and only if f of x itself is actually the 0 element of this field. So this forces f of x to be 0 for all x. And so the only function that satisfies that is the 0 function, which this proves that the f norm is positive definite. For symmetry, f norm of f minus g, it's the supremum of f minus g. Here we'll pull out -1, and we then use the fact that because -1 is a square root of unity, no matter what absolute value we happen to have picked, this has to have absolute value 1. So this becomes 1, and therefore we have symmetry. And so our map is symmetric. The triangle inequality follows like so. F plus g's f norm, well, this is the supremum of fx of f plus g. Fx is a seminorm, so it is linear. We can then add. And then here, this inequality is using the fact that the fx is a seminorm over big xf. And then we have this at supremum distributes, and we then get that this is the f norm of f plus the g norm of f, plus the f norm of g. Finally, we showed continuity of multiplication. This follows from the observation that for any f and g, the f norm of fg, well, that's the supremum of fx of fg. That's what this is the definition of that. Here, the absolute value is multiplicative. Supremum of a product is less than or equal to the product of the suprema, and then this we just rewrite, and that's that. So, as a result, we have that xfk is an example of a topological ring and a metrizable one at that. A topological ring TR is a topological space R equipped with an operation called addition and an operation called multiplication, which we denote by juxtaposition, so that R equipped with addition and multiplication satisfies the ring axioms, and so that addition, multiplication, and the additive inverse map are all continuous with respect to R's topology. A metrizable topological ring, an MTR, is a topological ring whose topology is induced by a metric. A complete metrizable topological ring, a CMTR, is an MTR which is also complete as a metric space. An isometry of MTRs is a map which is an isometry of the underlying metric space, a homeomorphism of the underlying topological spaces, and an isomorphism of the underlying rings. So, also the completion as a metric space, and any MTR can automatically be completed, and the completion of an MTR is always going to be a CMTR. Now, there's one subtlety here. Oh, so I went a little bit quickly. We require addition, multiplication, and the additive inverse map to be continuous. Now, in rings, there's going to be, a ring may have units, which are elements that have multiplicative inverses. Note that that then gives for any ring, we have the subring R cross, not the subring. We have the group R cross, which is a multiplicative group. It's a group under multiplication formed by all of the units of R. Since R cross is a subset of R, one would think that the natural way to take the topology that R has as a topological ring and then give that topology to R cross to make it into a topological group, one would think the natural way to do that would be the subspace topology, meaning that a set in R cross is open, that the open sets in R cross are generated by sets of the form U intersect R cross, where U is open in R. While this construction will, in general, make R cross into a topological space, it will not, in general, make R cross into a topological group. To see why this might be a problem, note that although, as I said, our definition of topological ring does mention the continuity of multiplication, it doesn't say that those elements of R cross, those elements of R, the elements of R cross, for which multiplicative inverse is a meaningful operation, our definition said nothing about that meaningful operation being continuous. So, just as defined up here, there is no guarantee that the group R cross with multiplication is a topological group. This is historically quite important, especially in number theory, because, as we will see in episode 8, a classic example of a topological ring R whose group of units fails to be a topological group when equipped with the subspace topology is when R is the Adel ring of a global field, in which case R cross is called the Idel ring, I instead of an A, and you have to do a little bit of work to figure out what the topology is. In fact, the standard recipe is not the subspace topology, but to do something called the diagonal embedding. What we do is we take R cross and we consider the embedding of it in the product of R with itself, where our embedding is the map which sends an element of R cross to the pair X inverse, where X inverse is the multiplicative inverse of X. Then we give R cross the topology that comes from this embedding as a subspace of this space where the product has the product topology. Now, as any functional analyst will tell you, one of the most important applications of vector space seminorms is in the construction of locally convex vector spaces. Since this construction works just as well for rings, we'll take care of it in one fell swoop by introducing the notion of a locally convex space. Let X be either a commutative unital ring or a vector space over a field for a field K, and let A be an indexing set, and let P be a collection of seminorms on A. These are going to be ring seminorms if A is a ring. this should be a collection of seminorms on X. This is going to be a collection of ring seminorms if X is a commutative unital ring, and it's going to be a collection of vector space seminorms if X is a field, if X is a vector space. For any point in X, any real number epsilon greater than 0, and any index alpha, we then define the ball of radius epsilon centered at X with respect to alpha is the set of all y in X whose p alpha seminorm distance from X is at most epsilon. But going back to what I said earlier about seminorms being induced by looking at components, you can think of this as saying that this ball contains all vectors whose alpha components differ from X by at most epsilon. The locally convex topology, LCT, on X, which is induced or generated by script P, is the topology that these balls generate through arbitrary unions and finite intersections. Then we have that a sequence in X is said to converge to a limit precisely when it converges to that limit for every alpha. Note, this is not required to be uniform with respect to alpha. It's strictly pointwise, and that is very important. More generally, a locally convex space, an LCS, will be a topological vector space, or respectively topological ring, which has the locally convex topology induced by a family of vector space seminorms, respectively ring seminorms. These are also known as locally convex topological vector spaces, LCTVSs, and locally convex topological rings, LCTRs. Two LCTVs, respectively LCTRs, are isomorphic if there is a isomorphism of the underlying algebraic structure, which is also a homeomorphism of the underlying topological spaces. So the advantage of this terminology is that when we combine it with what we've discussed so far, it allows us to give a very nice characterization of the space of functions compatible with respect to a frame. Let K be a global field, let X be a set, let F be a K-frame on X, and in an abusive notation, let's let F also denote the set of seminorms here. Then, 1. C of F, the space of compatible functions, can be given the locally convex topology generated by the seminorms in F, which makes CF into a locally convex space. X to the K can be given in the locally convex topology generated by the seminorms in F, which makes it into a locally convex space. And the best part is let V be the topological closure of this locally convex space. Then CF and V are isomorphic as locally convex spaces. In fact, they are equal as sets. That is to say, every element, the compatible function is precisely a function which is a limit of a sequence in this space that converges with respect to the locally convex topology introduced by this family of seminorms. From these follow from the fact that the f of x's are defined on CF and xk, respectively. So all that we need to do is to prove 3. And to do this, we're going to first prove the equality of the closure V of this LCS, is that V is equal to CF. So first let F be in V. Then F is either an element of xk, or F is a limit point of xk in the locally convex topology. So if F is in xk itself, then F is automatically a compatible function because F takes values in k, and k is contained in f of x for all x's. So let's just suppose F is a limit point. Then there is a sequence of fn's in xk, so that for Fn converges to F for every seminorm. This then we reduce is of course equal to this, and so now let x be arbitrary. This convergence, since this converges, in particular since this convergence implies that this quantity is going to be finite for all sufficiently large n, it must be that f of x minus fn of x is an element of the field big F of x for all sufficiently large n. And since the fn's are in xk, which is contained in CF, Fn of x is also in big F of x, and so if we then take this quantity, which is in big F of x, and add to it this quantity, which is also in big F of x, we then get the sum of two elements of big F of x, which is then in big F of x, and so this shows that little f of x is contained in big F of x. Since x was arbitrary, we conclude that f is compatible. So this shows that every limit point of xk in the locally convex topology I've given it is a compatible function. So conversely, let's suppose that f is a compatible function. To show that f is in V, it suffices to construct a sequence in xk which converges to f with respect to every seminorm in f in our frame, because then that will show that the function f is a limit point of xk and thus contained in its closure. So to do this, let's x be arbitrary. Since f of x has to be in the field big F of x, and since k is dense in big F of x, this is true for any completion of k, there is going to be a sequence of elements of k, axn, which converge in big F of x to little f of x. So for each n, we're going to define a function from x to k by the rule that fn of x is equal to axn. In other words, for each x, fn of x is the nth term of our sequence of elements of k which converge to f of x in big F of x. By construction, for any x in big X, the seminorm of this is equal to f of x minus axn, and since we constructed the axn's to converge to little f of x as n goes to infinity, this then, and since it occurs in this topology, that goes to 0 and we get what we want. So that means that this sequence of functions we've constructed converges in the locally convex topology to f, which proves that f is in V. And so this proves that every compatible function is contained in the topological closure of this locally convex space. So since these two sets contain one another, they are equal as sets. Now, with all that being done, we then get homomorphisms of their locally convex space structure, and we get by the inclusion maps. In particular, the inclusion map is going to be a homeomorphism and an isomorphism, and so therefore that means the inclusion map is an isomorphism of locally convex spaces, and so we're done. And in particular, note that xfk, equipped with the f norm, is then going to be a topological ring under the operations of pointwise addition and pointwise multiplication. So the difference here is, because this is a bit quick, in this case, we were working only with functions from x to k, and we did not require that they be bounded in any way. Now we're going to invoke boundedness. So remember that xfk is the set of all functions such that the f norm is finite. This is then going to be a topological ring under this, which is obvious. And so henceforth, as less stated otherwise, we're going to treat this as a topological ring with its topology given by the f norm and the associated metric space. Now, it's worth noting that we can also use the f norm on C of f. However, just like with xk, there are going to be compatible functions which don't have finite f norms. So we're going to need to make a subspace. Oh, this should be a superscript. So my bad. I'm going to fix this later. This should be a superscript. I'm going to define C BDD as it's the set of all functions with finite f norm. Then once we do that, we then have that C BDD of f is a metric space with respect to this formula. And then we then have that it's going to be it's going to be a metrizable topological ring. And now this brings us to our first big result. Before looking above, we just saw that if we take xk and give it the locally convex topology, and then take its closure, that's the same thing as the space of all compatible functions. Now I'm going to show that if we take this subspace xf, which is metrizable, and we take its closure, we're then going to get the bounded functions. That is, The completion of this metric space is in fact, it's not only is it going to be isomorphic to the bounded compatible functions, but but these two spaces are going to be equal as sets. So here, first, our proof is we're going to show that they contain each other as sets, and then it will follow that the inclusion map is from one to the other is an isomorphism, and we're done. Actually, it's not just an isomorphism; it's an isometry. So here, let F be in the closure of that space. Then, by definition, this means that there is a Cauchy sequence in XFK which converges to F with respect to the F norm. As is characteristic of frame theory, so Fn is Cauchy in this space. This means that for all epsilon greater than 0, there is an n epsilon greater than 0, so that whenever m and n are bigger than n epsilon, the F norm of Fm minus Fn is less than epsilon. Here, just taking apart the definition, this expression means that for every x in every point x, Fm of x minus Fn of x has an absolute value in big F of x, which is less than epsilon. So the Cauchyness of the Fn's in XFK tells us that for each x, this sequence is Cauchy in big F of x. But big F of x is a completion and of k, and so therefore it's by definition is complete. And so this is going to converge. And in particular, by construction, this limit must take the value of the limit of the Fn's in this limit here, and so everything works out to be equal. Indeed, we suppose that, and also moreover, we note that this result is independent of which Cauchy sequence we choose to obtain F. If we picked a different Cauchy sequence, then the two sequences would necessarily be Cauchy with respect to one another. They're getting very close, and so that would force them to vanish pointwise. Really, it's just all about arguing pointwise. Whenever something happens with respect to F norm, it means that we have pointwise convergence at every different point, and the supremum and the different semi-norms we've picked keep track of the different topologies. So the moral here is that the idea of a semi-norm is then what we use to formalize the notion of a choice of a topology of convergence for a particular point. So since F was arbitrary, now where does the boundedness convert? The boundedness comes from the fact that we can do this limit, it's uniform with respect to x. This holds for all x, so all of the formulas we're working with hold when we apply supremum with respect to x. So the f that we get isn't just going to be a compatible function, it's going to be a bounded compatible function. So now for the reverse. Suppose our function is bounded and it's compatible. We now need to show that it is in the completion of XFK. So for any x, just like we did with the previous proposition, since k is dense in big F of x, for each x we can choose a sequence Cn of x in k, which converges to little f of x in big F of x. In particular, we're going to choose our Cn's so that Cn of x minus f of x has an f of x absolute value less than or equal to 1 over n. And then we obtain a sequence of functions in this space by defining f of nx to be Cn of x. And now we just use a triangle inequality. Big Fx of Fn minus Fm is equal to this, which is equal to that. And then we're going to add and subtract f of x, break it up, and then we get that this is less than or equal to 1 over n plus 1 over m. So provided we choose m and n large enough, then that will make it, and particularly if we pick this, everything works out and it's very nice. Moreover, by our construction, when we take the supremums over x, because we dictated that for every x this has to occur, the convergence is then uniform with respect to x, and so everything works out, and we get that the Fn's converge to F in the F norm. And so, since our bounded compatible function is then necessarily an element of X Fk. Thus, these two sets are equal as sets, and so the inclusion map is then an isomorphism. Really, what the philosophy here is, that this is just an instance of a more general construction. if you have a family of semi-norms for each point in this, and we can use them to construct a locally convex topology, and then we can use the supremum of all of the semi-norms as a way of constructing a ring semi-norm, a ring norm. And as a result of that, we can then turn the locally convex topology into a metrizable topology, except at the cost that we have to throw out the functions in the locally convex space, which are not bounded uniformly. So for future work, rather than going directly with either of these spaces, it might be more useful to consider certain well-behaved subspaces. And as we will see in episode 8, the fact that we can realize the bounded compatible functions as a topological, in fact, as a metrizable topological ring is very important, because it means that we can study its ideals, which will in turn out to be intimately connected with our work with the PQ-adic linear-Tauberian theorem. And so just a proposition, just as an observation, let K be a global field, then the only situation in which the F-norm bounded functions will be equal to the set of K-valued functions is precisely if the frame assigns the discrete K with the discrete topology for all but finitely many X in big X. So this is an if and only if. Since big X Fk is defined as a subset, to show that this equality occurs, it suffices to show that Xk is contained in Xfk. So suppose that there is a finite set S in X, so that the frame outputs K with the discrete topology, the trivial absolute value, for all X not in S. Letting F be an Xk, note that for each X, f of X is in this field, and so has finite value. So that is, fx of f is a necessarily finite, non-negative real number for all x. The issue, of course, is whether or not these values are bounded uniformly with respect to x. To see that the bound is in fact uniform, note that since the trivial absolute value outputs either 0 or 1, we have that fx of f is going to be the trivial absolute value of f of x, which is always less than or equal to 1. And so, in particular, we then have that the f norm of f is going to be less than the maximum of 1, or whatever values the fx of f takes at those x's for which the frame spits out a non-trivial field. And then since S is finite, and since this is a finite set of real numbers, it has to be bounded, and so this proves that the supremum here is finite. On the other hand, if there are infinitely many points in X, so that for all n, f of xn is not k with the trivial absolute value, we can then we use the fact that since k is a global field, as a set, it's infinite, and so it's for each n, we can pick an element of k, yn of k or of f of xn, whose absolute value is arbitrarily large. And so we then let our function f of x, it's equal to yn if x equals xn and 0 everywhere else. Then at xn, this function has a semi-norm greater than or equal to n, and so that diverges when we take the supremum over all points in the domain. And let's just want to see if I want to get to this. No, I will cover this. I'll cover this later. So that's for the first part of this episode. Stay tuned for the next part.